Good afternoon. Thank you for coming. I'd like to thank organizers and the whole Node community for having me here. I also feel emotionally linked with the Node telescope, since it was the first I used during my PhD time ago. And I also have a point to make on its present and maybe on its future. First of all, what does it mean near-field cosmology? If you want to address fundamental questions such as elemental nucleosynthesis, the formation of the first stars, first galaxies, the yields of the first supernovae, you have two options. Or you go for high redshift observations, maybe with the James Webb Space Telescope, or you can do it locally in the Milky Way. This is the domain of the near-field cosmology. For instance, if you do high-resolution spectroscopy and derive elemental abundances from the most ancient objects we know in the Milky Way, globular clusters, all metal-poor stars, and dwarf galaxies, you can have an idea on the origin and the chemical evolution of the Milky Way. In particular, dwarf galaxies, classical spheroidal like Fornax, Sculpture, or even more primitive systems like ultra-faint dwarf galaxies, Reticulum 2, Tucana 2, or Sigue, are very interesting objects to study, and they provide very important clues about the history of the Milky Way. Unfortunately, these objects are typically distant, therefore very faint, and we can only have access to giant population in over-demanded facilities, likely 8-10 meters class telescopes with high-resolution spectrograph, say UVES at VLT, Horus at GTC, Mike at Magellan, and so on. And this is what we have been done during the past few decades. However, as Ricardo explained very well this morning, the outcomes of the Gaia mission are revolutionizing the field, since now we have positions and velocities for more than 1.6 billion of stars in the Milky Way. Just to show you an example on how powerful is the outcomes of the Gaia mission, let me show you this gallery of slides through the velocity space in the solar neighborhood. All the plots show the same. X-axis is radial velocity, y-axis is azimuthal velocity aligned with the rotation of the galaxy. And if you move to the right, you go to higher metallicities, and if you move from top to the bottom, you are gaining height above the galactic plane. If you focus in this metal-poor regime, you see this roundish shape, axisymmetric, and this is what we could expect from the classical view of the halo. However, if you go to higher and higher metallicities, it splits into two main components. One rotating population at about 200 kilometers per second, and underneath, in the shape of the sausages, another population that is show little to known azimuthal velocity, but a huge dispersion in radial velocity. Maybe it is more clear here. These are the residuals of the last major merger happened to the Milky Way some 9 to 10 gigayears ago. Just to illustrate this is a simulation when you see the early Milky Way and the Gaia-Sausage progenitor, the head-on collision and the subsequent tidal disruption. And then you see this picture that is kind of imploding and exploding in the radial axis anytime. So here's some facts about the Gaia-Sausage, also known as Gaia-Enceladus. It is the metallicity distribution function is peaked around minus 1.3 metallicity, but what I like to point out is the residuals of this engulfed dwarf galaxy are still around in the solar neighborhood. They are bright objects, and we can have access and study the chemistry of this single event that is nowadays supposed the 2/3 of the mass of the galactic halo. In other words, at moderate metal-poor regime, the halo of the Milky Way, are the residuals of this event. It is also very interesting to study different nucleosynthetic channels because they are providing different clues of the chemical evolution of a given system. For instance, if we measure sodium, aluminum, these elements are providing information very nicely supported by Rosa. We took observations of kinematically selected Gaia-Sausage members, and since they are closer than other typical halo or other ultra-faint dwarf galaxies or classical spheroidal galaxies, we have access to some candidates, some members that is doable with FIES and not. This was like very few months ago. My takeaway point, I think, not only has very, as we have seen this week, very interesting present, but it will have, for the next 2 years, very, very bright future. That's all. Let me just leave you with the most exciting feeling when you know that you can open the telescope and then all the sky and the sunset is for you from the node. That's all. Thank you so much.